Okay, today we're going to talk about growth and decay. And we've talked about growth and decay a little bit in terms of what they look like on a graph, and in terms of what our bases should look like. So if you'll remember, if b was greater than 1, that indicated that we had growth. And if b was less than 1, that indicated decay. So today we're going to start by looking at exponential growth. And we do have a formula for that. It's y equals a times 1 plus r to the t power. Obviously, t will be time, r is rate, a is some sort of constant, and then that should take care of everything. And we see exponential growth a lot when we talk about interest rates and compounding interest. So when you're taking out a loan and you need to pay it back, what are those interest rates going to look like? So let's actually go ahead and start by talking about compound interest, and that will lead us into our example. Compound interest is the amount of interest earned or paid on the initial investment and on the previously earned interest. So if any of you guys have bank accounts and you're kind of old school like me, I get a paper statement every month that says how much I put in my bank account, how much interest was paid, and then how much interest is paid year to date. So, maybe I put $4,000 in my account, and then over the course of the month, I earn maybe $5 in interest. And so the next month, I'm not just getting interest on that $4,000 I put in, I'm getting it on the $4,005 that I had last month. So I'm getting that compounded every whatever amount of time, okay? And there's different amounts of time we can get that compounded. So we'll start off with a real easy example before we get into the compound interest formula, which is a little bit more intense than the formula I just gave you. So the formula we just had would look something like this. Let's say my initial investment is $100. That's that A. And then I'm looking at a rate of 2.5% for 10 days. So if I plugged all these wonderful things into my formula, I would have y equals 100 times 1 plus r. And remember, we don't just plug in a percent like it is. We plug it in as a decimal, so 0.25 if I've moved the decimal over, and then at 10 days. And we're not going to do a heck of a lot of solving without a calculator because that would be very hard. We'll get it down to this amount, and then we'll start using a calculator to approximate, which would be $128.01 is what I have in my account now. Compound interest is a little bit more interesting than that. There's more to the equation for compound interest. Again, that formula is just for exponential growth. A compound interest formula would look like A equals P times 1 plus R over N to the NT power. And I will list out what each one of those things mean. A is my current amount. P was my principal amount, or my initial. R, of course, is my rate. N is going to be the number of times you compound. And T would be time. So, and the difference there is, you know, I may leave my money in my account for 8 years and it's compounded monthly. Okay, so monthly would be 12 times a year, or N equals 12, and then my time would be the number of years I leave my money in the account. Okay, so this formula would be really, really good to know. Okay, as well as the exponential growth formula we saw on the other slide. So let's go ahead and work an example with our compound interest. So let's say that your parents were thinking ahead when you were little, or maybe Miss Hawkins, who just became a grandmother, is thinking ahead and is creating a savings account for her grandson. So parents invest $14,000 in an account, and it is compounded monthly at 6%. And we want to know how much they will have by 10 years in. Okay, so the first things I'm going to always do is write that formula. And the more you write it, the better. So A equals P times 1 plus R over N to the NT. We don't know what they're going to have after 10 years, so that's going to stay A. My principal investment was $14,000 plus, or times 1 plus my rate, which is 0.06. It's compounded monthly, so that's N is 12 to the NT, or 12 times 10. Okay, I'm going to get this as simplified as possible before I go to put it in a calculator, because if you go to put this in the calculator, you're not going to get the right answer, because the calculator is very literal about order of operations, and so if you're not solving it down to something a little bit more simple, it's not going to work real well. Also, if I don't see all the work I'm going to show on a quiz or test, I'm going to count it wrong. So let's see how we do. We can leave the 14,000. I'm going to simplify 0.06 divided by 12 is 0.005. And if I just solve one thing per line, that's fine. Then if I add those together, I know that's 1.005. I could probably also solve that 12 by 10, which would be 120. We even know that from our extra math. And then I'm going to slowly use my calculator to solve a little bit more and more. So on my calculator, I have punched in what is 1.005 to the 120th. And I know from my calculator it's 1.82. Then I can multiply it by that 1,400. And when I do that, I get 25,471 and 55 cents. Okay. So the compound interest, that's how that works. It's actually very interesting in terms of what you can make your money worth in a couple years. A few things to note with compound interest. If it says it compounds biannually, that is every 2 years it compounds. So if I said I compounded my money biannually for 14 years, I'm only compounding 7 times during those 14 years. Versus semi-annually is twice a year. Okay. The last thing I want to look at here, we did exponential growth, which led us to compound interest. Now I'm going to want to look at exponential decay. Exponential decay, the formula for that is going to be very similar to your growth formula. It's y equals a times 1. This time we're going to do minus r to the t power. So let's say, for example, I'm going to compound at 6.6, or I'm decaying at 6.6%. It doesn't have to be related to interest. Sometimes in science you'll talk about radioactive decay with this formula. So whatever it is decaying at 6.6%. And I want to see how much it decays over 7 days. And maybe I'm starting with 4,500 cubic feet. So if I plug all those things into my formula, I'll start with y equals 4,500 times 1 minus 0.066 to the 7th power. And I'm, again, going to slowly use that calculator to solve. So the first thing I want to do is subtract inside my parentheses. When I do that, I'll get 0.93. Then I want to raise that to the 7th power. So I have 4,500 times 0.62 when I've raised that. When I multiply that through, I would get 2,790.33 cubic feet. Okay, so this is something where maybe my the amount of a radioactive substance I have is that 4,500 cubic feet, and it is decaying over 7 days at a rate of 6.6%. How much do I have left? Well, now I only have 2,790.33 cubic feet. So you can see I'm getting less than my original, whereas with the growth, I started with $100 and I ended the 10 days with 128. Okay, so that's kind of growth and decay. The difference is just the plus or minus r to the t power. Compound interest usually does not decay, so we only associate that with exponential growth.